Hello, today we will be talking about the generation of electricity. I want to start by showing you the sources of electricity in the USA. This was gotten from the EPA and it's the latest data that I have. So even though it's 2016, I don't have anything newer to show you guys, but I would like you guys to see that as of now, um, the biggest source of electricity in the United States is actually natural gas, which is approximately 34%. Coal is approximately 30%. Nuclear is 20%. Hydroelectric is 6%. And solar is about 1%. I also wanted to show you guys how electricity is used by sector. And so if we look at this, and this is also from the EPA, the industrial use of electricity in the United States is 25%. Transportation consumes 0.2%. Residential consumes 38%. And commercial consumes 37%. And again, these are 2016 data. This year, with the shift to everybody working from home, I don't know how much that's changed, but I could only imagine that the residential use has increased. Most of the electricity in the United States is produced in steam turbines. A turbine converts the kinetic energy of a moving fluid, a liquid or a gas, to mechanical energy. In the case of steam turbines, we're using turbines that have a series of blades mounted on a shaft against which steam is forced, thus rotating the shaft connected to the generator, which produces electricity. In this case, this drawing here, we see a coal power plant, and it is burning coal to create the steam. The steam runs through a turbine, which then spins a generator, and electricity comes out of the generator and goes into our grid. Now, I want you to understand that this drawing shows coal being burned, but for most conventional power plants, that is the way electricity is created, by boiling water and creating steam. A nuclear power plant does the same, but instead of using coal, it uses the nuclear fuel rods to heat up the water to generate the steam. And a natural gas-fired generator uses natural gas to heat up the water, but they all operate on steam turning a turbine. So again, power plants, steam is pushed through a turbine, which rotates a shaft. The rotating shaft drives a generator by turning a coil of wire in a magnetic field. 60 hertz AC electricity is generated at 25,000 volts. And we're going to discuss in a little while why we use alternating current in the United States and around the world. So what's the difference between AC and DC? In a DC, direct current electrical system, the movement or flow of electric charge is only in one direction and the voltage remains constant. In an AC, alternating current, the movement or flow of electric charge periodically reverses direction. An electric charge would, for instance, move backwards and forwards again, over and over and over again. This voltage fluctuates rapidly from positive to negative values. In a household electrical outlet in the United States, which is AC, the voltage fluctuates from negative 120 volts to positive 120 volts 60 times every second. So it's 60 hertz. The reason I call out in the United States, if you go to Europe, they are running at 240 volts and not 120 volts. So which of these two types of current is better, and why do we have these two types of current? So direct current is better when an appliance needs to run on batteries. So your cell phones, your computers, your laptops, your tablets, they actually run on direct current. Now, there are power transformers that change the alternating current into DC current that it needs it. Most of our electronics are running on DC. And when I talk about electronics, I'm talking about your televisions, your radios, those things. So an appliance uses integrated circuits. Most of these chips are designed to run between 5 volts or 12 volts of direct current. Alternating current, AC, is better when high voltages are required because the voltage can be changed using a simple device called a transformer. And also, if the appliance needs to run a motor, AC is better because AC motors are easier to build. So a little brief history of electricity and where these things came about. Electricity was first studied in detail in the 18th century. Many practical uses for electricity were invented by Thomas Edison in the late 19th century. The light bulb is probably his most famous invention, but he invented many, many things, and he also founded Edison Electric, which is now General Electric, and they used DC or direct current. In many of the cities, a lot of the homes that first had electricity were operating on DC. Later on, Nikola Tesla, who was a physicist and actually worked for Edison, developed AC. And AC's biggest strength is that it can be efficiently transferred over large distances, whereas DC tends to have more losses if we try to transmit it over long distances. To prove that AC is dangerous, Edison built an electric chair, which was used. Eventually, AC became the industry standard, and it stays that way till today. And in the United States and in New York, actually, you could see we do have electricity traveling long distances because we still get electricity in this area that's coming down from Niagara Falls, which is, on the other side of New York State, many miles away. And if it was not for the AC, we would not be able to transmit electricity that distance. So how do we transfer electrical power? So we use wires, and they're used to transfer electrical power, and they hopefully have a small resistance. Or R is what we use to represent resistance in the equations. And we have an equation that power loss is equal to I squared R, where the I is the current, R is the resistant, and P is my power loss. Because high voltage is better because more power can be transferred with less current. So as an example, if I have a power plant and I want to transfer 1 megawatt through a line with a resistance of 1 ohm, and the voltage is 1200 volts, what is the power loss? So first find the current using P equals IV, and which is the same as I equals P divided by V. So I is equal to 1 million watts divided by 1200 volts, which is equal to 833 amps. So the power loss, which is equal to I squared over R, would then be 833 amps squared times 1 ohm, which is 693,000 watts. So if you think about that, if I'm transmitting that voltage at 1200 volts, I'm losing almost 70% of the electricity that I generated is being lost. So in example 2, I want to transfer that same 1 megawatt with the same line resistance of 1 ohm, but now I'm going to do it at a voltage of 120,000 volts. So what is my power loss? So again, I'm going to use P equals IV, and by doing that, I could solve for I, my current, to be 1 million watts divided by 120,000 volts, which is 0.833 amps. So to find my power loss, I use the equation of P equals I squared R, and P is equal to 833 amps squared times 0.1 ohm. Well, I'm sorry, that should be times 1 ohm, is 69.4 watts. So you can see that is a much smaller loss. So I mentioned earlier that when we're working with AC, we could use transformers that will change the voltage, either a step up and go higher voltage or a step down to go lower voltage. So a transformer is an electrical device that takes electricity of one voltage and changes it into another voltage. They only work for AC circuits. Basically, a transformer changes electricity from high to low voltage using two properties of electricity. Electromagnets, in an electric circuit, there is a magnetism around it, and electromagnetic induction. Whenever a magnetic field changes by moving or by changing strength, a voltage is made. So they're constructed by winding wire around two ends of a rectangular piece of metal or the core. Generally, that's made out of iron. And electricity moving through the primary coil creates a magnetic field around the core. This magnetic field induces an electric field and moves electrons in the secondary coil, thus producing an electric current. The input line connects to the primary coil, while the output lines connect to secondary coil. The alternating current in the primary coil induces an alternating magnetic field that flows around the metal core, changing direction during each electrical cycle. The alternating field in the core, in turn, induces an alternating current on the secondary coil. The voltage of the secondary coil is directly related to the primary voltage by the turns ratio, or the number of turns in the primary coil divided by the number of turns in the secondary coil. In this picture, you can see that I have my AC source and I have a primary coil that's wound around, and then I have on the right side of this drawing a secondary coil. And so to figure out my induced voltage, I would have my voltage that I have going in times the number of coils in the secondary coil divided by the number of coils in the primary coil. I mentioned earlier that we have step-up transformers and step-down transformers. Those are the two types of transformers. And a step-up transformer converts a low voltage to a high voltage. And in that case, there are more turns on the secondary coil than there are on the primary coil. A step-down transformer converts high voltage to low voltage. So in that case, there are less turns on the secondary coil than there are on the primary coil. So for example, if you want to increase your house voltage from 110 volts to 220 volts in order to power your electric stove, you could use a transformer with twice the turns in the secondary coil as in the primary coil. So 110 volts, and I'm going to say I have 5 turns, is equal to 222, which is equal to 220 volts and 10 turns. I'm going to include the links to 2 videos that go into a deeper explanation about transformers, and I would like you to look at those when you get a chance. So the grid, electrical power travels from the power plant to your house through a system called the power distribution grid. In this diagram that we have here, this little picture, we have a power plant and we have a transmission substation, which then goes to our high voltage transmission lines. And then when it gets closer to a neighborhood, we have another substation and it kicks down the voltage somewhat. And then it's transmitted on poles in this case, sometimes underground, and there are transformers. And then the transformer brings that voltage from the lines down to the voltage that is entering your house. In the continental United States, the power transmission grid consists of about 300,000 kilometers of lines operated by approximately 500 companies. So this example of the power grid, and you can see where our lines are going all over the place. And you also could notice here that there is a very, very heavy amount of lines where there is more population. So a power plant generates about 25,000 volts. The power station steps up the voltage to 345,000 volts, so it could be transferred through power lines. So the question of why not transfer electricity at a higher voltage? Well, for one thing, air is not a perfect insulator, and at very high voltages, arcs of lightning would shoot between power lines and the ground. Safety is also an issue, and I have a note here that birds could land on a bare wire because they do not create a closed circuit, so there's not a path to the ground. But if the voltage was higher and higher, we can have a path to the ground just through the air. So an area substation, it steps down the voltage to 100,000 volts. And then a distribution substation, and these are stuff that are closer into your neighborhoods, will then step the voltage down again to 20,000 volts. And then a step-down transformer outside your house steps the voltage down to 120 and 240 volts. So in a typical house, large appliances like your washer, dryer, and if you have an electric oven tend to run at 240 volts. I have two links here. They will also be on Blackboard, so you guys could please look at these videos that describe wind and solar in the first one and nuclear energy in the second one. So what are the problems with the US grid? I'm going to start by saying that we've all dealt with blackouts and service disruptions. Just this past summer, I live up in Yorktown, and I was without power for 4 days following the tropical storm that came through here. And that is an issue. So the current hardware is old and needs to be replaced, and we're going to have large blackouts and service disruptions likely in the future. Also, 65% of electricity is lost between generation and distribution. So low efficiency increases both the need for fossil fuel and the amount of pollution and greenhouse gases emitted. The other issue is that our grid cannot easily accommodate renewable sources such as wind and solar power. So I have a question here of what is a smart grid, and I do have a video that will be on Blackboard so you can get a little better understanding of a smart grid. But the benefits of a smart grid are that it will actually give us less blackouts, reduced greenhouse gases, improved air quality, and also is designed to work better with alternative fuel sources. So according to research sponsored by the US government, improving the efficiency of the national electricity grid by 5% would be the equivalent of eliminating the fuel use and carbon emissions of 53 million cars. This could be accomplished by implementing a smart grid that links all aspects of the electric grid together from generator to consumer with sensors and smart devices in order that we will eliminate, in order to provide enhanced operational capabilities that will eliminate waste, incorporate alternative power sources, solar and wind, and improve reliability. Smart grid technology will also allow customers to sell electricity they generate from rooftop solar panels and other renewable sources back into the system, which will be able to locally store energy, incorporate intermittent sources like wind and solar. So one of the issues right now with wind and solar is that they do not produce electricity all the time. As an example, if you have solar panels on your roof that are generating electricity, we have a period of the day that we call night where there's no light. And those solar panels at that point are not producing electricity. And even during the day, the amount of electricity they can produce changes based on the weather conditions. If it's a bright sunny day, then they will be producing a lot of electricity. If it's a cloudy, stormy day, then they will be producing less electricity. And similarly, wind turbines are designed to operate at a certain amount of wind. So if we do not have that wind, they won't be turning and they will not be providing electricity. So using smart grid technology, a home would be as likely to be powered by electricity from a neighbor's rooftop solar panel or a windmill on the edge of town as it would be from a power plant 50 to 100 miles away. Under the current power grid system, utilities don't learn about power outages until their customers call. Smart grids will be able to diagnose themselves as well as monitor electricity demands in real time. That is a big issue in itself because I will tell you that they don't know if you're out of power unless you call or unless your neighbors call. And then they'll send someone over and start to investigate. So I'm one of those people that when the power goes out, I report it because I don't know if my neighbors will. Or what if my neighbors aren't home and they don't report it? We could be out of power for a longer period of time because the electric company doesn't even know we're out of power. So using smart meters, customers will be able to monitor their electricity use online and get suggestions for minimizing it, either by turning off certain appliances or using them at different times. There are areas that also have different rates night and day. So just using the electricity at nighttime may save people money. So what are the obstacles and why do we not have the smart grid now? Well, estimated cost of building the smart grid is actually approximately $165 billion, or about $8 billion a year for the next 2 decades. On top of the staggering cost, there are also many different competing interests involved in smart grid technology. Upgrading the energy grid will require state utility companies, new upstart energy firms, local and state governments, and federal authorities to work together. Trying to get all of these entities to partner up may be even harder than actually raising the funds. Having worked in both local government and for a utility company, I could tell you that getting everybody to work together is probably the single biggest obstacle to this. And then the money that it needs to run is also very, very difficult for these companies to raise. So those are the obstacles. I will have a video link in Blackboard that describes the smart grid a little more for you.